Hello, I'm Tom Wildman, and I'm speaking to you from my home. And I want to share with you a very important situation that's going on here that you need to know about now, and that you will meet again in future instances when you are a environmental engineer. And the situation is this: you you are going to look at results today and this week uh, that were generated by someone else. The waters were sampled by someone else, but you have to feel confident enough about those results so that you can present them to a client in a confident manner. And so I would like to talk about how these results were generated. Talking about the inductively coupled plasma atomic emission spectrometer and the ion chromatograph. Kate Spangler should come in here and talk about the ion chromatograph, which I think she'll tab on to the rest of this video. And so uh, let me start by showing you a short video, 7 minutes, done by a Perkin-Elmer representative, sort of showing the ICP AES instrument. Okay, now on this, I'm going to tie this in right now and start it on YouTube. Yeah, here it is right here. Okay, let's see what they're going to say.
Good water. Ever wonder what's in your water? Well, different elements, when in solution, have characteristic colors to them. Copper has a characteristic blue color, and that's because most of the red portion of the spectrum is absorbed, so we see blue. However, we're going to use this general principle to analyze different types of elements in different types of water samples using different types of analytical technology. Hello, and welcome to the Lab Report. I'm your host, Paul Krampitz, and today we'll be talking about the analysis of water using an ICP plasma spectrometer. In order to do the analysis of water, we're going to need some sort of heat source, sort of like a lighter here. This is a butane lighter. It burns at about 8 to 900 degrees C, something like that. Commercial flames that you might be familiar with, like welding and acetylene torches, they can reach temperatures of 3,500 degrees Kelvin. However, we need something even hotter. We're going to be using an argon plasma, like we use on the Optima ICP system. The plasma itself is hot ionized argon gas with a mixture of electrons in it, maintained by an induced magnetic field. And an induced magnetic field is probably very similar to the first experiment you ever did in school, where you took a battery, you wrapped it around a nail, and you picked up graphite shavings. What did you do? You made an electromagnet. Well, this whole system that creates the plasma actually creates temperatures of 10,000 degrees Kelvin, or hotter than the surface temperature of the sun, believe it or not. When we introduce water into the plasma, it quickly converts the liquid into a solid, into a gas. So soon you have a gaseous mixture of elements that were actually in your water. Now, each one of those elements has a nucleus surrounded by shells of electrons. When it hits the plasma, those electrons in the different orbitals are excited and they jump up to a higher energy level. But when they go back down to other transitions or where they came from, they'll emit the energy they got in the form of a photon, which is inversely proportional to the wavelength. The optics inside the ICP will then separate these photons by wavelength and then correlates the signal to that of a known calibration standard for concentrations to quantitate the metals. The ICP system and autosampler system has a lot of tubing, in length that is, so you may be able to see all this tubing here that has to be rinsed out when you're doing an analysis. So if you're going from a very concentrated solution to another sample that doesn't have much of that element in it, you may have an issue, right? You may not have rinsed out what's in the sample prior to what you're doing now. So what we use is something called a fast valve. This application uses a 1 mil loop that can be rinsed out at about 25 liters a minute with a very quick rinse. Instead of about 90 seconds to rinse all the tubing out, this system only needs about 7 to 10 seconds to rinse out that loop. Now, we used an ESI fast system in this application note that basically reduces your sample to sample time by half. Now, for environmental laboratories, that's a huge productivity gain because you get paid per sample, right? The next thing that you have to worry about when we were talking about all these different elements here that we're having in the solution, whether it's copper, nickel, iron, cobalt, chrome, you have a very complex spectrum, or can. For example, just iron has thousands of emission lines itself. Add in chrome and nickel and others that have a lot of emission lines, and very soon you have an incredibly complex spectrum. There's a pretty good chance that those lines are going to overlap or interfere with the elements or the analytes of interest that you're trying to measure. The Optima system has the best resolution on the market for a simultaneous ICP system. Besides the excellent resolution of 6 picometers at 200 nanometers that the Optima has, the Optima is also the only unit to employ a correction that handles both complex backgrounds and spectral interferences at the same time. This technique is called multi-component spectral fitting, or MSF. It's basically an MLS deconvolution technique coupled with something called Kalman filtering, which handles very complex backgrounds and removes that as a component. This is an EPA-approved method for 200.7 and can be superior to probably what you're familiar with now, which is interelement corrections, or IECs. MSF, since it's modeling out different components in the spectrum itself, one of the main things that analysts have trouble with running complex matrices is to get rid of all the noise. You can have photon shot noise. You can have all kinds of different noise sources that actually shows up in your blank. Well, MSF models those noise components out. What that gives you is a twofold increase in detection limits or lower detection limits. ICP is an excellent work source technique for waters and wastewaters and conforms completely to EPA 200.7. The inclusion of a fast system that we talked about with the 1 mil loop, and that's all you have to rinse out, that can double your productivity. And MSF, if employed, can remove interferences, and by taking out the background noise, can result in lower detection limits. So please, at the end of the presentation here, click on the link and it will take you to the application itself with all the details, which is basically a standard operating procedure, an SOP, that includes all the lines, all the QC checks, all the calibration standards that you need, and is basically a recipe for you to follow to make it much easier for you to do 200.7 in the analysis of drinking waters and waste. Well, that's our...
Okay, here I am back again. You see that we had the video concerning the PerkinElmer instrument as basically the instrument we will use to generate your results for metals. And I want to go back and look at some of the things that this fellow from PerkinElmer said so that I can amplify just what's going on. So I'm going to share my screen here. Let's see if I can find what I need. Here it is. Okay, let's look at this. Okay. All of you have used fireworks at one time or another, and you're wondering where the colors came from that come from the fireworks. Well, those are elemental gaseous elements that have been excited and then do the emission of the various colors. Like strontium will give you red, and so that's how these happen. Also, maybe at one time or another you threw some. You had some salt enter a gas flame and you saw this orange excitation that I was showing right here. Well, let's explain where that what has to happen to get that orange excitation from sodium chloride. You're going to start out perhaps with a sodium chloride solution. Then you have to put in enough energy to get it into a sodium chloride vapor right here. And then you have to put in more energy in order to make atomic sodium. Well, when you make atomic sodium, then it's going to be, then you're up to maybe 1,000, 2,000 degrees Kelvin. But now you have to make all the elements in the periodic table be a vapor, and so that's where this 10,000 degrees Kelvin that the plasma generates, which the fellow was talking about. With that, with being at such a high temperature, and you just have atomic sodium, what will happen is the electrons will start boiling off this atomic sodium, and it will go into an excited state like such. Then they will return to the ground state right here, and then upon going to the ground state, they will have this 589 nanometer. Let's see if I can get rid of that here. Well, anyway, I can just leave it there. This 589 nanometer emission line that you see here. Now, this emission line, that should be in the visible spectrum, will be separated into into individual lines in the spectrometer, and we will pick out those individual lines and figure out what elements are in your sample, and by the strength of the line, we'll be able to tell how much was in the sample. And so that's what we're doing with this ICP AES. There's two really great things about this method of doing an analysis. The first is that we use the spectrometer to do the separation of all the lines, and it does such an excellent job that we can analyze 30 elements at the same time simultaneously. And the next thing that happens is, because this is an excitation, I can analyze solutions that may go from 10 micrograms per liter all the way up to maybe 100 milligrams per liter, 4 orders of magnitude, and not have to do any dilutions or anything. So it's a very robust instrument. And so it has really revolutionized how analysts do atomic spectroscopy and get so many results that are so good. Okay, now I'm going to stop this again, and I'm going to pause. Okay, here I am back again. And what I want to do now is look at the results, which you shall have concerning the concentrations of the metals in your samples. And so I'm going to go back in here to screen share here and pull up this Excel file. And this is what you shall begin to, this is what you will see as far as inductively coupled plasma atomic emission spectrometer results, something such as this. If I pull this, if I make this small, you can see that there are lots and lots of columns of numbers and the like, and so this can be quite overwhelming. So I want to explain what the readout looks like. So I'm going to go back, zoom in again here, like about there, okay, and explain what's going on. Okay, let me like that. Okay, let's see what we have here. This would be the typical computer output. Here you have the elements that we have analyzed, and I think there's around 33 or 31 elements here, as you see. This is the emission line that we use. There is the sodium, that 589 nanometer line, as you see here. You don't need that in your results. We just have it because in some cases, like magnesium, we have two lines in here just in case. Okay, so that's the first column here. The second column you have here are the detection limits for each element. So that the detection limits, for example, for sodium are 0.0193 milligrams per liter. These results are in milligrams per liter. It says it right up there. Okay, some of these elements can be analyzed very very low levels. Here's manganese, and it can be analyzed to 0.2 micrograms per liter. So that's really very sensitive line for that. Next, now you will see some standards here. You have CCV metals and CCV non-metals. We run these standards to see how things are going. They'll be, I think in your case, they're going to be between 1 and 10 milligrams per liter for these metals and non-metals. You'll see that. And then the 1643 that we run is a sample that comes from the National Institute of Standards and Technology, so that we can use that to measure the accuracy of what we have as far as our samples are concerned. So that's the first 3 or 4 columns within this. You might, I think nowadays we are also running a background here every now and then, a blank, to see how well things, see how well backgrounds look. So that's the first thing you see. Up here in this dark blue area, these dark blue columns, rows that you have here, we have internal standards. We monitor the argon in the plasma. And for an internal standard, we have scandium lines right here. Now these scandiums will be, should be about 100%. That is that they're, that they're right on if they're 100%. Some of them maybe be a little high. Here's one that's 104 right here. And so what will happen to these results is this scandium measuring 104 will be adjusted back down to 100, and all the elements that use that internal standard will be adjusted back down to 100. Now this says R, so if I pick one out here, so there's one, boron, right there, that's an R. And so this will be adjusted just a small amount, decreased a small amount, because the internal standard read 104 instead of 100. And that will be included within your results. All those things will be adjusted for when you get the results. And so these are the elements that you have. As I say, sometimes we analyze 2 samples, two lines for one element, like magnesium is a good example here. It is so very, very sensitive that we have to put it in another line, because oftentimes magnesium might be running about 100 milligrams per liter, and it will swamp out the more sensitive line. Okay, so we have that too. Now, another thing that's very important here, this is my old freshman chemistry teacher situation coming up, and that is, let's look at this calcium line right here. Okay, this calcium line says that the concentration is 28.2830 milligrams per liter. Now, that just cannot be. What cannot be is that we cannot analyze anything to that degree of precision. That's 1 part in a million. And so that really can't be done. When people ask me about how good our results are as far as inductively coupled plasma atomic emission is concerned, I tell them it is if the concentration of the element is 10 times above the detection limit, there's the detection limit. So If it was up around 10 times, it would be about 0.2. This is 28, so that's far above 10 times the detection limit. This result would be good to plus or minus 10%. Okay? Well, plus or minus 10% means that that I might be able to, I can quote 1 part in 10. So, you know, I can use 2 significant figures, sometimes 3 significant figures, but never 6 significant figures. And so it is very important for you in this situation to make certain that you trim these numbers to the number of significant figures that you're comfortable reporting on. Like, you know, this one you might not have to trim at all, that chromium, because that's 3 significant figures. But this one you have to trim quite a bit. Because if you don't do that, then your client will automatically assume that you know this number to 6 significant figures. And you don't. And so you can't do that, you know, you can't do the comparisons that maybe you would like to do if you had a more precise result. And so it's very important you trim these so that they do not overinterpret the results. I know from experience that when we give these practice presentations on Tuesday, there are going to be some results that I will see that will come out. You know, you put down the 6 significant figures. And of course, I will ask, how do you know that it's good to 6 significant figures? And you'll say, oh, I don't know. And so there you are. You have to make certain that you only report the results to the certainty that you're confident with, which is plus or minus 10%. Okay, I think I'm going to stop there, and then I will let